wait, there's no, the temperature is not the same either, huh?
So this is current, this is power.
Okay.
Current and power. You have the voltages, you have the currents. Sorry, you have the voltages, the current, and this is the power at different biases.
No, that is,
Small print.
Right.
it is,
So but you have them all there. So this is for you to do your own calculation if you have time. So this is was shown already in the past, but this is an updated version. You have a measurement of a non-irradiated CNN sensors with a bias voltage, which was 50 volts, so it's a 5 times depletion. And here on the left you see the temperatures versus time. This is days, so it's 5 days. And you have the current versus time. So this is showing that was an automatic measurement with the variation of the temperature. You still are keeping a reasonable, let's say, constant value over the period. The measurement was taken, by the way, at 25 degrees plus. So then, of course, we had monitored the current and temperatures as best we could do during the test beam. And this is the longest working period that I could collect with similar conditions. This is one of the CNN, 34. It was one of the proton irradiated 5 times.
with respect to that, the fact that between the top curve and the second curve from the top, you have roughly a factor of 2, and you have a 7 degrees change. It tells you that it's pretty well thermally coupled, I believe, because it's exactly the difference you expected, but from 7-degree changes. So I think that the thermal coupling is quite good there.
Well, I think this is probably the value that you should really compare this one, because we did it on purpose at a certain moment. And this is after a moment where we really could go down to to around minus 20. So the comparison between the on and off is there. And then some more tests were done with the neutron irradiated here at CERN in the climate chamber. So thanks to members of the CERN group. So again, the resistor was on the aluminum plate. The bias voltage was 190 volt because we had quite a huge voltage drop here. And I think motivated by the fact that the temperature that you see here is minus 15 measured. So there could be, of course, some differences. The electronic chip was on. And this is the current that was measured. And this is over a couple of days.
I think I'm losing my mind. It's not a question for you, Cinzia. It's probably for the previous speakers. After the same dose, you also run your planar sensors at minus 15 degrees Celsius with a 1,000 volt supply. How much was your leakage current? I'm being lazy. I don't want to go back to the slides.
I don't think we went to 1,000 volts when it was at the beginning. We went to 800 volts maximum.
Well, what was the current at 800?
I can tell you now. Oh, I'm sorry.
Sorry, Cynthia, I'm being lazy here.
Not sure. So I can tell you that here, in this condition for us, it was 390 microamps.
It was 555 microamps. Minus 15 on the plate at 800 volts.
Thanks.
Then, of course,
So,
I think one would really see the thermal cycling and rapid thermal cycling, because if there is any problem related, there are two devices reported here. One is a non-irradiated with a bias voltage 20 volts. One is the 2 times 10 to the 15 proton irradiated with a bias of 50 volts. This cycle was quite rapid. We made 6 cycles for a total of 60 minutes per cycle. 10 minutes ramp up and down, 20 minutes +5 and -20. The measurement was taken at -20 and once at +5, and in the two cases. And I think the message here is that from the beginning at -20, this is 22 nanoamps in the case of the non-irradiated. At the end of the last cycle was 23 nanoamps. In the case of the irradiated, it's 55 microamps at the beginning and 53 microamps at the end. The +5, those are the two values, 180 nanoamps non-irradiated, 867 microamps in the case of the 2 times 10 to the 15. I think, well, normally if you look in the literature, this type of test would be done over days, I would say even months. So please take the significance of that. We tried at least, and we didn't say at least.
Just to be clear, I mean, the other thing you're clearly looking for in doing such a cycling is, as you said, whether you see any bumps failing.
Sure.
I mean, you mentioned the current, but were you able to assess whether or not?
No. We did not. Listen, we finished literally.
I just
Sunday
wondered
morning.
whether one could look at
Yesterday
some raw
morning.
number like noise and see if it was unchanged.
No. Let's say the only thing we could really check at that point was the leakage current.
Okay, fine.
And but of course now these devices will be remeasured. I think it would be nice to do that with a 5 times 10 to the 15. This is what you want, and you want to go down really probably get even to the point where you see the failing, because this will give you an indication of the lifetime. And probably not even with one sensor. You would like to do that with several sensors.
Yes.
So let's say we have that in mind, and at least accept at least the attempt at that stage, because it was really done in a very
No,
short
I
period of
completely
time.
understand. I was just wondering whether any of the other things which one might be able to measure reasonably quickly, whether one had data already. But
Sure.
your colleagues are saying that might even be possible on a short time scale. So
Sure. Well, I would say that this exercise was extremely important because it gave us a list of things that we definitely would like to see, and to see much more extensively, because
okay, thanks.
Can I quickly use the chance, Gino, to give you some information that you asked for? I just had to look it up. So we looked up, for example, a run of SEC51, which is the sensor that I was showing, where we glued the PT1000 to. And this was run without, with front and off at 125 microamperes at 600 volts. And the temperature reading of the temperature sensor attached to aluminum was at minus 20.8 degrees C. And then we switched the front end on, and during the data taking was somewhere between 360 and 380 microamperes. And the temperature reading of the temperature sensor changed to minus 18.9 after some time. And this was the sensor which had at minus 12.3 degrees C 370 microamperes at 1 kilovolt. So it's exactly the same sensor. This is why I think this might be a good example, so one could try to do the calculation and guesstimate how warm it might have been during the test beam.
Thanks.
okay, so I think we are getting into one of the hot parts of the presentation here, which is the quality control and ear strip. So we have at the end 80 strips measurements that are giving us quite a good indication of even more local failures, like looking at the photo overall.
So you're going to be talking about some collision that you're analysing, or
Some data, some shower shapes analysis we do.
okay?
Efficiencies kind of.
How do you decide which event to pick?
Just one we know about.
What do you okay.
Something that was that the three of them could talk, because otherwise they have their own.
Yeah.
So you each
So
has got
we
one event.
initially discussed, and now we're trying to instruct Francisco and all these things so we can properly.
Okay.
So it could be a real discussion.
Could be a real discussion. Okay, excellent.
That's the point.
I think the lighting is good, isn't it?
It's perfect. Lighting is perfect.
Maybe I will.
She's going to put makeup on you in a minute.
Well, this we can leave it because it's the Argentinian yerba.
Ya está bien, ahora voy a ver si puedo,
Están las tres charlas abiertas, igual. La de Fran del Trigger, la última esa que tiene el 12-20 y el boost
Fran,
from
no,
Left,
no,
capítulo.
Lo que vamos a hacer es hablamos de esto y después chido y la trigger efficiency para estos fotones y
Claro.
pasamos a la otra charla.
A la de
No sé cuánto tiempo hace.
Está bien. No sé si está...
Y encima acá hablamos para estar un poquito así. Como que así como estoy dando la charla.
Every time I come to CERN, I meet somebody I last met 15 years ago. I've been here for so long that, but some people have been here a very long time. Okay, if you just turn over,
Just,
you start. You start.
I'm recording.
You're recording. Okay, close.
Bueno, en esta, acá la eficiencia, tenemos en las 4 regiones del detector para fotones y la idea que se ve acá tendrá la ineficiencia bien en el forward region. Y el problema
Pero
social
para,
es
vuelvo a ver un poquito. O sea, acá estás mostrando que se te haría fully efficient a
arriba de
arriba de
100.
100. De 100 GB.
Arriba de 100 donde ya las llaves son bien con línea. Y el problema en el último, en el forward, encontrás estas, que es el W3, la variable de fotones, viste, seguimos analizando, son 3, es el width cuando viene el shower en el calorímetro, deja el width en el primer compartment. Y ese tenés un problema de reconstrucción, ves en el tail. Este es datos y este es en Monte Carlo. Si ves los problemas de reconstrucción, entonces el corte que debía ser fully efficient está bien en el core de la distribución. Entonces te queda ahí, pero si mueves el corte ahí es donde te queda bien resuelta.
Y o sea, acá estás definiendo el fudge factor a partir de la diferencia que tenés entre el mean value de la distribución de datos.
Tal cual. Tenés las dos distribuciones, Monte Carlo en datos, y ves la media de las dos, y si shifteas ahí donde la eficiencia te queda bien, entonces esa es la buena onda, ahí ves el shape de los dos, el ratio diferente de los dos, entre Monte Carlo y datos. Para las 4, y acá en el tercero es donde tenés más eficiencia.
Ah, ahí está mostrando las distintas regiones de ¿está bien?
Claro, tenés los distintos colores, hay diferentes regiones. Entonces cuando corregís eso, ahí es donde esto se te va arriba. Entonces ahí podés reconstruir bien.
Bien. Y ahora,
Y esa es la-
cuando en este tipo de plots, cuando estás mostrando datos, ¿estás aplicando algún trigger?
el trigger de fotones. Eso es lo que estudiaste vos, ¿no?
Sí, ahí está la charla.
¿Qué trigger se usaba?
El G22 luz. Y la del G20 luz. Estas dos son las Canon Card. Del level 1 y del high level trigger. Y la de eficiencia versus ETA.
Te queda justo
arriba de 20, claro.
La cuarta.
Ahora para la del level 1 estás usando con el minimum bias stream. ¿Está bien?
Sí, y un más.
Bien. Claro, entonces ahí se ve que arriba de 20 ya tenés full efficient.
That's probably enough of the general.
Presentó Martín el otro día en el meeting del Standard Model. Acá te fijaste en la eficiencia de selección de fotones para las distintas regiones de aceptancia del detector. Tenés el corte en isolation de 3 GB y fíjate, bueno, en la región, entre la región más forward del detector, la eficiencia decae un poquito, fíjate que teníamos 95% y acá aproximadamente 90%. Fíjate que acá en esta comparación tenemos datos todos los datos de 2010, 36 puntos y pico más. Y fíjate acá cómo se diferencia lo que esperábamos con Monte Carlo, lo tenés en el histograma en celeste, con el histograma en datos, ¿está bien? Entonces, a partir de...
Sí, pero ahí lo tuneaste.
Claro, no. Y bueno, hay que hacerlo dar. No, pero cuando lo hiciste eso, volvé. O sea, acá, ¿cómo corregiste? O sea, ¿corregís con una transformación lineal? ¿Moviste?
Sí, lineal, lo simple. Trabajar las dos distribuciones,
Sí.
pero una las echás a la otra. Para que te y ahí justo te queda.
Está
la
bien.
eficiencia de nuevo en el pelo.
Hasta que lo hicieron dar, básicamente.
Sí, o sea, ya está eso se te fue.
Claro, ahí ya moviste el efecto que tenías antes. Está bien.
It just wants to get you tapping the keyboard here.
Great.
El G20 luz y el G22 luz, las Turner Curve y la eficiencia con respecto a esta.
No, esto fue en el meeting de Higgs.
Eso es para Higgs, pero bueno, es el mismo trigger.
¿Te preguntaron mucho después de esto?
No, sí, algo me preguntaron.
Pero al final la eficiencia da bastante bien, ¿o no? O sea, porque acá tenés la obra de eficiencia.
Sí, la eficiencia va bien y además nos podemos
buenísimo.
revisar esos datos, la mejor.
Pero sí, ya lo ves ahí. Me queda full.
Do.
Just talk, just say
talk,
same
okay.
conversation you had, anything.
Ok.
Just like as if I'm not there.
Some amusing photons.
Amazing. Sí, vamos.
¿Tenés ahí para ir a la última charla?
Yeah.
I can shut this to reveal that.
Acá presentaste
Esta es la del Marcello,
Sí.
de las dos.
Does that
Se
work?
le agregan
Yeah.
define todas las dos contribuciones. Ahora tenés 1 y 2.
Esta
Esta de fermentación.
One fermentation.
Tenés uno de ESR y el otro de Final Stage.
Update again. Religious, is it a religious symbol?
I hope not.
Because sometimes it's just you'll be remitting,
Committing a sin.
You'll be not even that.
I
if
just
you want
look at it as a sculpture, that's all.
okay,
Of course, yeah.
it's far.
But you need to zoom in to the 6th floor.
Yeah. Zoom out. recording.
Okay, Kato. Can you tell me first what you are meeting here to decide?
Okay, this is the committee meeting to decide what kind of detector we want to make. And we, at the moment, trying to build a pixel sensor, but there we have the two technology, and there's the two competing technologies. So this committee decides which one is appropriate for our detector.
Okay, and can you just say briefly what the two technologies are?
Both, yes, both are made from the silicon, and it's a pixel. That means it's something like 2 centimeter diameter. There's a lot of pixels inside, and one called the planar. It's more or less standard nowadays, but the other one is a 3D. It's like a 3-dimensional, and it's more aggressive technology.
And is there space for a 3D sensor? Is
Yes,
there enough space?
Yes. Well, the geometry is almost same. The thickness is also same, so both are fits.
I don't understand. How can the thickness be the same if it's 3D?
Well, it's okay, I think that we should say.
It's only a small amount of 3D.
Yeah, it's not a thin, well, very thin detectors. It's like a 2 centimeter, and the thickness is only 0.2 millimeter.
Okay.
And this side we call it's a 3D. The electrode is either vertical or something like horizontal.
Horizontal. Okay. Okay. And what is the format for this decision? You say the committee.
Yes.
You're in the chair.
Yeah.
So what is the structure?
Okay, so in the committee, okay, we have the, okay, this decision is made inside the atlas, but we like to hear the many wide opinion. So we have the two members from the other experiment, namely from the CMS and ALICE, and we have the 4 experts from in the atlas also. And okay, the developer of that detector is not the member of the committee, so that we are more or less neutral people.
It's interesting you have people from the other experiments as well.
Yes, I think we need, because, okay, the technology is new, and we like to have more knowledge from the many people in the world. So
Interesting. And how do you decide? What are the criteria?
okay. We are planned to install this detector in 2013, and we have to make sure that we really have the detector at that time, and also that the detector should survive till say 2022, and we have to make sure that the detector survives for this long period. And in LHC we have a lot of collision. So that we get a lot of particles, so that we have the radiation damage, so that we have to make sure that detectors survive with that harsh environment.
Okay, and how does the committee decide? Do you vote or do you get a consensus?
We try to be a consensus, and in a closed session we will discuss and what will be, okay. I think if it's a black and white, it's easy. But in reality, in some part, one choice is better, and the other other choice is better. So we really have to assess everything, and then I hope finally we like to make a consensus.
And you have to reach a decision tomorrow.
Yes.
So it is a bit of work to do
Sure.
to do that.
Yeah.
Okay. Is anyone winning at the moment?
Well, we will discuss now, so
Okay,
we don't know yet.
So just describe briefly, you have an open session and a closed session.
Yes.
At the open session, anybody can come.
Essentially, yes. Especially for the people who work for that detector can come, and it was very useful that these people are there, because there is a lot of professional, so that in some questions some people can, only the expert can answer, so that I think it's better to have such a meeting open, so that the people can see what's going on.
Okay, now we now come at the end, we come to the closed session.
Yes.
This is, you still have another open session
Yes.
to come. So you will try and narrow down the criteria?
Okay. In today's closed session, we first summarize what we heard from today's, and we again rate that what is the issue for one detector and what is the issue for other detector, and to understand that what we should hear more details. Then tomorrow we may again ask some questions to clarify these things. Then I hope we can decide tomorrow.
Okay, and one final question.
Yes.
Are you giving out money in this decision, or is it simply policy? In other words, are you actually allocating money, resources, or are you simply deciding on policy?
You mean I myself? Okay.
Well, the committee of which you are chair.
Yes, okay. We are not the resource committee, but we are the science committee, so that we just check the technology and make a recommendation. And the resource discussion is done in other board.
Okay.
Another board.
So when you make a recommendation,
Yes.
is it automatically accepted?
Well, it's not automatically, but actually on Wednesday we will have that collaboration board for this detector, so that finally they will decide on Wednesday, hearing our recommendation.
By this detector, you mean the pixel detector?
Pixel detector.
For the Atlas upgrade?
Yeah.
Yeah. Okay.
Okay.
Thank you. Time for your coffee.
Thank you very much.
Thank you. Don't run away.